All right, so we basically came up with a better punchline to the age-old joke right before lunch. Why did the chicken cross the road? Because chickens can't teleport. Yeah. So you got your chicken. You got your chicken standing here. This is your chicken. C for chicken. Well, let me use darker. C for chicken. And the yellow part is the road. And he's trying to get to the other side. That's his objective. So why did he cross it? Well, how else was he going to get to the other side, I ask you? He can't teleport. So the joke has always been misunderstood. Like, why did the chicken cross the road? Like, people answer the joke trying to surmise the motivation behind, the chicken's desire to get over there, when that's not what the joke is about. The joke was the chicken has to get to the other side of the road, and how is he going to get over there? He's going to cross it. Why did chicken cross the road? How else are you going to get there? Chickens can't teleport. IVT, right? IVT. So next time that joke comes up, you explain it and give the new punchline. Maybe explain the IVT. Duh. You got to cross it. Okay. So here's a nice example. That's maybe better than the chicken joke. If you measure the outdoor temperature on your back porch, not mine, to be 47 degrees Fahrenheit, man, wouldn't that be nice right now? At 8:15 in the morning, and then you measure the temperature at the same spot 4 hours later to be 62, right? Same spot, same instrument. You take all the variables out of it, same place in the sky where you measure whatever. 47 at 8:15, and then at 12:15 just after lunch at 62. Explain why there has to be a time somewhere between 8:15 and 12:15 where the temperature on that back porch at that spot had to be exactly 51.351 in punto degrees Fahrenheit. Your thermometer may not be that accurate, but yet you still know it had to be that, right? Why? Y'all wouldn't disagree with that, right? Okay. So why is that? What'd you say? It had to pass through it, right? By the IVT. Temperatures can't teleport. Chickens can't teleport. Temperatures can't teleport. By the transitive property, chickens are temperature. No, that doesn't work. No, there's lots of things that can't teleport. There's no way to get from 47 to 62 without passing through every temperature in between at least once, including 51.351, or as accurate as you want to be, right? So that's the IVT. And now it says, based on the two readings, is there a way to determine the exact time that that temperature occurred? What time? You tell me then. What time between 8:15 and 12:15 did the temperature equal that? Can we determine the time?
Well, no, there's so many.
No, this is an existence theorem. It tells us that this temperature had to exist. Now, we know there had to be a time. That's the X value that's guaranteed. This Y value is guaranteed. It's also guaranteed to have occurred at an actual moment in time, right? That's the X part. The X value is guaranteed, but we don't know what that X value is. There's no way to determine that without knowing anything else about the situation in between. If we had more data points or something, we can like fit a statistical curve to it using least regressions or whatever, and then kind of interpolate. But there's no way to know. It's an existence theorem, okay? So let's go ahead and write out why we know that. We would say since the temperature is continuous from 8:15 a.m. to 12:15 p.m. inclusive, okay, comma, there had to be a temp of 51.351 degrees Fahrenheit at some time between 8:15 a.m. and 12:15 p.m. Now, the theorem itself does allow for the time for it to occur to be an endpoint. But in this case, we know that it's not going to be at 8:15 or 12:15 because we know what the temperature was at that time. And it's 51.351. I'm sorry, bless you. It wasn't 51.351. So in this case, we know that actually the X value has to occur on the open interval somewhere between those two times. Now, could the temperature have been 51.351 several times? Yeah. Could it have risen above 62 degrees sometime during that time? Yeah. Could it have gone below 47? For sure. We don't know anything about that. All we know is pick any number between 47 and 62, and we know sometime during that 4-hour period, the temperature had to be that at least once, okay? At least once. So it's guaranteeing a Y value and an X value. Don't know where it's at. Why did the temperature cross the road? To get to the other side. No, because temperatures can't teleport. I'm working on my jokes on my conference period now. Officially not during this class. Sorry. I didn't mean to be thinking out loud. Okay. No, I do have a shirt that I'll wear sometime. And when I wear the shirt, you'll know the shirt that I'm talking about. That's all I'm going to say. Landon already knows. I should have worn it today, but it's college day. And the shirt I'm talking about is not a college shirt. All right. Example 6. I'll try to remember to wear it tomorrow. But tomorrow's game day. Tomorrow's superhero day. I'm not wearing the shirt tomorrow. Maybe Friday. Piecewise fun. That's right. Tomorrow's superhero day. Determine if the IVT applies to the following function on the following intervals. Explain specifically why or why not. I don't think we're going to finish the notes today, guys. I'm going to try, but it doesn't look like it's going to happen. Looks like the worksheet's going to be due on a Friday, the day after a big game. We may have to talk about that too tomorrow. Yeah, right. So look at this. Determine if the IVT applies. What's another way to rephrase that? Yeah, just to see if the given function is continuous on the given closed intervals, right? It's the exact same thing. For a function to apply, the if part has to be met. I think in geometry you had that. It's called the Law of Logical Syllogism. And it's basically a theorem that says in any if-then statement, if the if part is true, then the then part is true. It's like, wow, that's a great theorem. So yeah, if the IVT is going to apply, the if part has to be true, meaning that function has to be continuous on the closed interval. If not, we'll state why. So this is like a masked or hidden continuity question. All right, from -4 to -2, piecewise function. -4 up to -2. Well, if you look, for the entire duration of that interval, we're on that top piece. Yes? Including at the right endpoint. Would you agree? Because it's not just less than -2, it's less than or equal to. So we know we're going to be riding that line up to -2, and then we're going to dot the end of that graph. So the question is, if I know it's going to work at -2, will it work at -4 and everything in between? Well, it depends on what the function is. 2x plus -2x plus 1 by itself is a polynomial, right? Which is continuous in general where? All real numbers everywhere. So yeah, it's going to be continuous in any closed interval. So this one is yes. We'll say yes. Yes, because, or since is shorter, since f is continuous on the closed interval from -4 to -2. That's simple. Now, if that inequality up here had been strictly less than -2, and on the next piece it started at -2 less than or equal to, now we would have to check the right endpoint. We would have to see if the function value, using the second piece, would be equal to the limit value from the left. Well, we don't have to do that because it's the same people that's building the road coming in from the left and the bridge. Well, we get lucked out there. All right, how about from -3 to 0? Well, -3 to 0 starts on the top piece and ends somewhere on the second piece, right? Because 0 is somewhere between -2 and 1. So now I have a potential problem here if I want it to apply. It looks like I'm going to be able to start at -3 and cruise all the way up to -2, no problem. So that gets me up to -2. But now I got to get from -2 to 0. I need to check. I need to check what? Yeah, will it work at 0? Let's do the right endpoint. Will it work at 0 automatically? If 0 is on the interior. Well, again, that depends on, yeah, it's x squared plus 1, which by itself is continuous everywhere. So I know that that's going to work from -2 up to 0 and including 0. But what I don't know is what? At -2, it could be a jump, right? It could be a jump. I need to see if it's continuous at -2. So continuity now on an interval turns into continuity at a point. Let's do it informally. The limit and the function value at 2 and from the left of 2, vice versa, -2. How about it? The limit from the left at -2 and the function value at -2 by direct substitution are what? Into the top piece? 5. That's 2 to the 3 already. What's the limit from the right of -2 plugging into the second piece? Also 5. Does 5 equal 5 equal 5? Yes. So is this function f continuous at -2? Yes. So we start at -3. We cruise up to -2. At -2, we're good. We continue on the same road, and we cruise up to 0 along the parabola. And we stop at 0, and it's on the interior, so we're good. So is this function continuous on that interval? Yes. Yes. Yes, comma, since f is continuous on the interval from -3 to 0. Man, we got it twice in a row. I guess they're all going to be yes, huh? That's how life works. A pattern of 2 means a pattern of, right. The sun came up the first 2 days of my life, January 27th, 1974, and January 28th. And it's been coming up every morning since. Patterns. Ignorant overgeneralizations. All right. How about on the interval from -1 to 1? Well, let's see. Where are we starting? Which piece are we starting? -1. The second piece, right? -1 now is somewhere between -2 and 1. So we're starting on the interior of x squared plus 1, which is continuous everywhere on its own. So is the left endpoint okay? Yeah, we'll be able to get the left endpoint no problem because we're on the interior of the parabola. We're going to be able to cruise up to 1 and not include it here. And we want to cruise all the way to, well, 1. So I'm going to get the open interval up to 1. But because the function value is defined by the piece below it, I do have to check, right? I don't have to check the limit from the right of 1 because I want 1 to be a right endpoint. So I just need to see if the limit from the left equals the function value. What's the limit from the left of 1? 2. What's the function value at 1? 3. Caramba. Does 2 equal 3? No. So it works on the open interval. It just doesn't work at the right endpoint. So no, comma, since, and we got to be specific, since f is not continuous at x equals 1, which is relevant because epsilon, that is in the closed interval. That's the best way to write it. It's very specific. We're listing that it's not. We're listing because it's not continuous at this specific place. And oh, by the way, that's a relevant x value because it's in the closed interval. It happens to be the right endpoint. Because if it wasn't continuous, let's say at 2, that wouldn't even matter because that's not in the interval. All right, y'all do the next 2 on your own. You got it. You got the idea. Okay, so part D. We're going from 1 to 4.5. 1 is starting on the third piece. And there's an equal sign there. So we're cruising to the right. So we're good. We're good at the left endpoint. We don't even need to check the value. Okay. And we're cruising to 4.5. Well, 4.5 ends on the second piece. So we need to get past 4, don't we? We need to get past the exchange. So real quickly, the limit from the left of 4 using the third piece is 6. And the limit from the right of 4 and the function value at 4 are the bottom piece, which is also 6. So f of x is continuous at x equals 4 because 6 equals 6 equals 6. So cool. We start at 1, no problem. We start cruising. We get to 4, no problem. We pass right through 4. And when we get to 4.5, is it okay? Can we stop there without any issues? Well, that's something to consider because we do stop on this last 4th piece here. Look at it. There's only one value of x where this is not defined, and it's where? 5. This function piece has a vertical asymptote at 5, and only 5. So it's continuous everywhere except 5. So if we only need to cruise up to 4.5, which is before 5, are we okay? We're okay. So this would be yes. Yes, comma, since, or because f is continuous on this interval. But now notice if we're trying to go from 2 to 7, I'm still starting on the third piece, which 2 is between 1 and 4, so that's no problem. I can get past 4, no problem, for the same reason. But now I got to stop at 7. 7 itself is no problem. The only problem is 5. There's no way to get from one side of 5 to the other side of 5 and finish at a nice 7 without passing through the non-removable infinite discontinuity. Okay, so this would be no, since f is not continuous at x equals 5, which is relevant because that is in the closed interval from 2 to 7. So this one fails because the open interval doesn't work, not because of one of the endpoints doesn't match. It's the open interval. All right, so kind of nice. Instead of asking you to check for continuity on an interval now, I can just ask if the mean value theorem applies. Continuity on a closed interval. All right, questions on that one? What else can we do with the mean value theorem? Well, quite a bit, actually. We can use the IVT to prove the existence of a value without actually finding the value, okay? So let's look at example 7. The velocity of a particle. We're going to be talking about particle motion like 3 different times in this class this year, like in depth. This is just kind of one example. Velocity of a particle moving horizontally along an x-axis, okay? So it's moving left and right, left and right. You could say the x-axis is the track it's moving on. Positive velocities means that the position is increasing, which means it's moving to the right. Negative velocity means the position is decreasing, which means the particle is moving to the left, just an FYI. The velocity is a continuous function. You got t in seconds and v in feet per second. And we have selected values given below. Explain why there has to be a time on the interval from 2 to 5 where the particle is at rest. For the particle to be at rest, what are we looking for? Are we looking for it laying in bed, or what's that? Yeah, it's very specific constant. Yeah, 0. If the velocity is 0, it's not moving. Even if it's for just a single moment in time, we say it's at rest. So notice it says to say why there has to be a time strictly between 2 and 5. That just means that it's not going to be at rest at 2 or at 5, which it's not, right? If you look at the chart, at 2, it's a negative velocity. So it's moving to the left at a ½ foot per second. At 5, it's not motionless. It's moving to the right at 2 feet per second. We still have to say that the function is continuous on the closed interval for the IVT to apply. Well, if it says that it's given by a continuous function, and that's all it says, it doesn't say for all real numbers, guess what's implied? All real numbers. If it says it's a continuous function, you can assume all real numbers. So let's go ahead and say since v of t is continuous on the closed interval from 2 to 5, beefy bracket 2 comma 5. Or you could say like this, 2 less than or equal to t less than or equal to 5. So again, they're not going to give you the equal signs up above, but that's fine. You're trying to use the theorem, and it needs to be continuous on the close. I'll show you why right after this. All right, so now we got the theorem on our side, don't we? Now we got the theorem on our side. If I'm looking for a particle to be at rest, that we already said that's going to be where the velocity is 0. So let's go ahead and write that. We've taken a verbal description and we've turned it into a numerical equation. Well, now I have a y value that I want to look for, namely 0. It's not in the charts, but what do we notice? To the left, or at the left endpoint, we have a negative number, and the right endpoint is a positive number. Isn't 0 an intermediate value between any negative and positive number? Yeah, hence the name intermediate value theorem. So you could say this now. Since it's continuous on the closed interval, comma, and since negative 0.5 is less than 0 is less than 2. This is the linchpin. Once you state that the theorem is on your side by stating it's continuous on the closed interval, that's the linchpin. That's the intermediate argument. You're literally going to write a compound inequality with the smaller of the endpoint values on the left and the larger the endpoint y values on the right. The left endpoint is not always the smaller one, right? It is again here, but you know, if they had been flipped around, we always want to put it in increasing order. And then the value that we're interested in finding, in this case, it's the one we defined, goes in the middle, in between, in the intermediate, okay? So it looks kind of like the squeeze theorem, right? But it's not. Now, you could put strictly less than there because it's true, but you're not, you could also put less than or equal to if you want. That doesn't really weaken the argument at all, okay? And since then, now you could say, comma, by the IVT, you don't ever have to say the name of a theorem that you're using. But I would like for you to do that because it shows me that you know what the theorem is. If you actually just use the theorem, that's good. But when you sprinkle the name in there, you know, it's like seasoning on the food, right? You could eat like bland food, but it's not, right? But you take that bologna and sprinkle some seasoning on it, and now it's bologna. Okay, by the IVT, and then all you have to do is come back up here and say this. This is going to be the pain in the butt. But you know what? It's all right there. There must be a time 2 less than t less than 5 where the particle cramp is at rest. That's a common thing that we're going to use for all the VT theorems. We're going to get it on our side by stating that the if part, you don't have to prove that it's continuous. You just got to state it. Now that the theorem's on your side, what's your linchpin argument? In this case, it's the inequality, showing that the value that we want is intermediate between the smaller and the larger. And then by the name, and then you use their words. Okay, easy. I mean, it's, now, do we know where between 2 and 5 it's 0? No. We just know it's impossible to go from a negative number to a positive number through a continuum without passing through 0. At least once. Okay? Questions on that? All right. Tomorrow we'll finish 8, 9, and 10, and then we'll look at the lowest scoring free response question in the history of AP Calculus College Board. Okay? And we'll see why.